When we look at this next problem, we don't see the same kind of pattern as on the previous one that we could factor by grouping. So I need to use my rational zero theorem. So my possible zeros will be the factors of the constant term divided by the factors of the lead coefficient. Since the constant term is negative 10 and the lead coefficient is 1, the possible zeros will be plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Since my lead coefficient is a 1, I will only have a 1 as a denominator. So now I can start my process of trying to find the zeros. So I'm going to use synthetic substitution. So if I use 1, I will get 1, negative 3, negative 8, negative 10. 1, negative 2, negative 2, negative 10, negative 10, and that's negative 20. So I do negative 1, 1, negative 3, negative 8, negative 10, 1, negative 1, negative 4, 4, negative 4, and that's 4, negative 6. And I do 2, so 1, negative 3, negative 8, negative 10, 1, 2, negative 1, negative 2, negative 10, negative 20, so this would give me negative 30. So I do negative 2, 1, negative 3, negative 8, negative 10, 1, negative 2, negative 5, 10, 2, negative 4, negative 14. So then go for 5, 1, negative 3, negative 8, negative 10, 1, 5, 2, 10, and 2, 10, 0. So I just found my 0 being 5. Since my 0 is x equals 5, the first factor will be of p of x minus 5. And the second factor, of course, comes from the second part, which is x squared plus 2x plus 2. So now we know that we'll have a root of 5. And our second factor, the x squared plus 2x plus 2, is not factorable. So I am going to use the quadratic formula to solve that. So negative 2 plus or minus the square root of 4 minus 4 times 1 times 2, which is 8 over 2. So after simplifying, this is negative 2 plus or minus the square root of negative 4 over 2. And if I simplify, it's negative 2 plus or minus 2i over 2. So the roots will be negative 1 plus or minus I. So one of my roots is going to be, the real root is the x minus 5, so x equals 5 is my real root. And my two complex roots are negative 1 plus or minus I. So then we go for this next problem where we have p of x equals x to the fourth minus x squared minus 2. So the first thing I do is find the possible zeros. Possible zeros are plus or minus 1 and plus or minus 2. So I'm going to start my process of finding the zeros. So I start with 1, and it's 1, 0 for the x cubed term minus 1 x squared, 0 for the x term, and negative 2. So 1, 1, 1, 1, 0, 0, 0, negative 2. Then I go for negative 1, 1, 0, negative 1, 0, negative 2. 1, negative 1, negative 1, 1, 0, 0, 0, 0, negative 2. Then we go for 2, 1, 0, negative 1, 0, negative 2, 1, 2, 2, 4, 3, 6, 6, 12, and 10. And the last one is negative 2, 1, 0, negative 1, 0, negative 2, 1, negative 2, negative 2, 4, 3, negative 6, negative 6, 12, and 10. And since I could not find a 0, that means this polynomial will not have any rational roots. So no rational roots. Of course, if I try factoring this polynomial and write negative 1, negative 2, negative 2, and 1 over x squared, I could use my factoring to find my actual roots. So the factored form of the polynomial will be p of x equals x squared minus 2 times x squared plus 1. So I can find the other type of roots, and if x squared minus 2 equals 0, then x squared would be 2, so x would be plus or minus the square root of 2. From the second factor, which is right here, x squared plus 1, if I subtract 1, x squared equals negative 1. So from the second factor, I would have a 0, actually 2 zeros of x equals plus or minus I. So I just don't have enough room to write anywhere, so I wrote the zeros here and here for the factored form. So which would mean that we have two complex zeros or imaginary zeros right here, and we have two irrational zeros because they are plus or minus the square root of 2. And now we are going to talk about the Descartes' rule of signs. The number of positive real roots of a polynomial arranged in descending order can be found by using the Descartes' rule of signs. The rule uses the number of variations in sign, that is, the number of times successive coefficients have different signs. Descartes' rule of signs. The number of positive real roots of a polynomial p of x with real coefficients is the same number of variations of sign of p of x, or less than the number of variations of sign of p of x by a positive even integer.